Have you ever wondered how shots like the ones in the video are possible, or how they just seem to defy what we know about physics? In the next couple of minutes, we will explain how these tennis ball interactions follow the same rules as everything else. To start, the speed that a tennis ball has depends on its acceleration. The acceleration of the ball across the court is determined by Newton's second law of motion, F equals ma. When a player hits a tennis ball, the force of the racket is directly proportional to the acceleration of the tennis ball due to a constant mass. Additionally, Newton's third law states that for every action there is an equal and opposite reaction. If the racket is held still, the tennis ball will receive a force equal to that exerted on the racket. This explains why a player can feel the force in their hand when hitting a ball. As the ball hits the racket, the impulse is very high. This large change in momentum is due to a large force being applied over a small amount of time. This idea is why the velocity vector changes and allows the ball to be launched back in the opposite direction with more speed. The racket loses velocity upon colliding, while the tennis ball increases in speed. And now we'll explain this with formulas.
Hello! As explained earlier, Newton's second law, which relates force, mass, and acceleration, is one of the major concepts for why tennis works. Now in our case, force is directly proportional to acceleration. This is because the mass of our tennis ball is constant. This means that if I hit the tennis ball with a large amount of applied force, I'll get a larger amount of acceleration as a result. Whereas if I just tap the ball gently, my applied force is small, so that my acceleration will also be small. Now, since the tennis ball comes in contact with the racket for a short amount of time, we can use the concept of impulse to relate this force and time. Since our time is small, our force is very large. This is because impulse is the integral of force over very small time steps. This is all equal to the change in momentum. Now, with the change in momentum, we can look at the conservation momentum, which relates the initial momentum with the final momentum. In order to use the concept of conservation momentum, we need an isolated system. Now, our system is isolated because it is elastic and because we are going to ignore the effects of air resistance and friction because it's for a very small amount of time. Now, this results in the total momentum being conserved. Now, using the conservation momentum equation, which uses the concept that momentum is an object's mass times its velocity, we notice that since the racket has a larger mass compared to the ball, for each step of velocity that it decreases, the ball will also increase in its own velocity. Now, with all of these concepts, now you know why these little green balls fly.
Many people who do not play tennis might think to hit the ball with the racket flat. However, to increase the odds of winning, many pro players differ from a standard hit by applying spin to the ball. There are two main types of spin that can be generated, topspin and backspin, or called underspin. For topspin, the racket is pointing towards the ground and the racket is brushed up against the back of the ball. This causes the top of the ball to rotate away from the racket as the ball leaves. Backspin is the exact opposite to topspin. The racket is face up and the ball is brushed down the back of the racket. This causes the ball to rotate towards the racket as it leaves.
So to calculate the ball flight time, what you need to do is you need to calculate the velocity vector components. So to do that, you take the initial velocity times cosine theta to get Vx, and the initial velocity times sine theta to get Vy. And what we're going to do is we're going to assume Vx is constant because we're going to ignore air resistance. Then what you do is you come over here to this equation, which is a standard kinematic equation, and we're going to say y sub o is how far you hit the ball off the ground, theta is the angle you hit it at, and y is when the ball hits the ground. So if you do that, you can assume y here is 0, and then what you're going to do is you're going to use the quadratic equation, which is negative b plus or minus the square root of b squared minus 4ac over 2a. And this equation will give you two answers. Whichever one is the positive answer is the answer you're going to use, and that's the ball flight path. And then you can calculate how far it has went in the x direction by taking your initial x, which we're going to assume is 0, so this would be initial x, and this is going to be your final x. So you take 0 plus the velocity in the x direction times the time it took for the ball to fly, and this will get you how far away your ball landed from where you hit it.
If the ball is hit with spin as it flies through the air, a strange thing happens, which is called the Magnus effect. This effect happens when an object is rotating within a fluid and the object is moving relative to that fluid. Here is the equation and some explanation.
So now we're going to learn more about the Magnus effect. The Magnus effect is a force exerted on a spinning object moving through a fluid. So obviously we're dealing with a tennis ball moving through the air. So a tennis ball having some tangential velocity with topspin, it'll be rotating the same way, the top will be rotating the same way as the velocity. So as it moves through the air on the bottom of the ball is pulled up the back of the ball due to the ball's rotation. Due to Newton's third law of pair, every action must have an equal and opposite reaction. So as the air is being pulled up the back of the tennis ball, the air must exert a downward force on the tennis ball. This, however, does not happen the same with the air coming across the top of the ball. This is because the rotation opposes the way the air is trying to flow, therefore the air is not pulled down the back of the ball. This causes a downward force on the ball. For backspin, this is the exact opposite case, because the air on the top of the ball is going with the rotation, so the tennis ball is exerting a downward force on the air, and so the air must be forcing an upward force on the ball, and the air along the bottom, of course, is opposing the rotation, so therefore there is no force caused there. This can be determined mathematically with this equation, where F sub m is the Magnus force, lowercase omega is the angular velocity, v is the tangential velocity, and s equals the air resistant coefficient across the surface of the object. Now, with all this knowledge, you know how these little green balls fly through the air.
The way a ball hits the ground can be very useful in tennis. A flat hit comes in and hits the ground and leaves at the same angle it came in. This makes the shot very easy to predict and not very useful for tennis. Shots with topspin and backspin differ greatly in how they bounce compared to the standard flat hit. When a ball hit with topspin lands, the rotation is in the direction of motion. For the ball to leave the ground, the ball must have the same translational motion as it does rotational motion. When the ball leaves the ground, it will always have topspin. When the ball comes in with topspin, the amount of work the ground must do to match these two is not a lot. This results in the horizontal velocity of the ball to increase, which causes the angle at which the ball leaves the ground to be less than the initial angle. For backspin, the ground must change the spin of the ball, increasing the work the ground must do and the time the ball must be in contact with the ground. Because of this, the amount of horizontal velocity is diminished compared to the vertical velocity. This causes the leaving angle to be greater than the initial angle.